Hey everybody, this is another Uncertainties compositions problem. This is a little bit more realistic and interesting. Here we have a solid cylinder that's released from rest at the top of a slope with a constant gradient. That's a constant slope. A stopwatch and ruler are used to measure the length that it travels and the time that it takes to get down the slope. The uncertainty in the length of the slope is 2%, and the uncertainty in the time it takes to roll down the hill is 8%. We need to find the percent uncertainty in the acceleration of the cylinder and the velocity of the cylinder at the bottom of the slope. So this is an interesting one. It only actually gives us two givens. And our givens are going to be, well, it's the percent uncertainty in the length, so it's delta L over L, but I'm actually going to call it delta S over S, because you may notice that since it's rolling down a hill with a constant slope, it's going to be a constant acceleration. So this will be uniformly accelerated motion. We'll be able to use kinematics to solve for it. So I'm going to use my kinematics variable for displacement, S. Delta S over S is equal to 2%. And we're also given our uncertainty in time, delta T over T, percent uncertainty, is equal to 8%. So we need to find our unknown is percent uncertainty in acceleration, so that's delta A over A. And we also need to find the percent uncertainty in the velocity at the bottom of the slope. So our final velocity we could call either V final, VF, or just V. I'm going to use the IB notation, so that would be delta V over V. And we're not actually given any numbers, so we can't get any absolute uncertainties, but we're going to use what we know about the situation to figure out how to find the percent uncertainties. So first of all, we have two given variables from our kinematics equations, basically S and T, and we need to find either A or V. So we need to pick the situation, we need to pick the equation that matches the variables that we have. And actually, there is one other given that's not quite explicit, but it's the fact that our cylinder is released from rest. So we are given the fact that the initial velocity is equal to 0. And I should use the IB notation, and in the IB, our initial velocity is U. U equals 0. So we can find the correct equation for the acceleration, for example. And that's just the kinematics equation with S, T, U, and A. And our displacement equation is 1. Displacement is equal to V naught T, or UT, I guess, UT plus 1/2 AT squared. But since our initial velocity is 0, this is actually going to simplify to S is equal to 1/2 AT squared. So from that equation, we can actually solve for A, and we get A is equal to 2S over T squared. This is, well, A is a function of displacement and time, and since there's no addition or subtraction, it's just multiplication, we can use the rule for adding and, well, we can use the rule for multiplying to get the uncertainties of products and quotients. And the rule is we add the percent uncertainties, or add the relative uncertainties of all of the input variables we have. Here our input variables are S, T, and actually T again. So we can say that our percent uncertainty in A, delta A over A, is equal to delta S over S plus delta T over T plus, since it's T squared, delta T over T again. And that's going to give us, well, percent uncertainty in S is 2%, so that's 2%. Plus 8% for T, 8%, plus 8% again. And the percent uncertainty, delta A over A, is equal to 8 plus 8 plus 2, which is 18%. Awesome. Now, the other thing we need to find is the percent uncertainty, or the fractional uncertainty, in the final velocity v. Now, since we know the percent uncertainty in A, we could actually use pretty much any kinematics equation we want. However, since uncertainties always increase when you compound them, if we use this uncertainty from A to calculate our final velocity v, or the uncertainty in our final velocity, then we're going to get a much higher uncertainty than if we were to use our raw values, displacement, raw uncertainties, displacement, and time uncertainties. So it's best if we use the equation. It's best if we use the equation that has s, t, u, and v as our only variables. We don't want to have to deal with a super high uncertainty in A. So there is an equation, and it's the average velocity equation for uniformly accelerated motion. That equation tells us the average velocity, which is u plus v over 2. That happens to be the average velocity if you're accelerating at a uniform rate, times time is equal to our displacement s. But u is 0, so we end up with vt over 2 equals s. And that simplifies to v equals 2s over t. v equals 2s over t. So there's our equation. We can then, well, we see that our final velocity is just the quotient of, it's 2s and t. So there are two input variables. Since it's a quotient, we're going to add the percent uncertainties. So our equation is going to be delta v over v. Delta v over v is equal to delta s over s plus delta t over t. Now you may ask, what about that 2? Why don't we count that 2? And we can count that 2 if you want. We could say plus the uncertainty in 2 over 2. But the uncertainty in 2 is 0. There's no uncertainty there. It's just a number. We know it's exactly 2. So that goes to 0. Anytime we have an exact number, that has 0 uncertainty. So we can actually just plug in our answers. Delta v over v is equal to, the uncertainty in s is 2%, plus the uncertainty in t is 8%, which gives us a total uncertainty, delta v over v, of 10%. So there's a quick little example of how we use equations to figure out compounded uncertainties. Thanks.